Modern enterprise networks pull in and distribute immense volumes of data every second. Information continuously routes through a massive, interconnected web of servers and databases. This is a geographically dispersed cloud platform. Instead of a centralized server rack sitting in a local basement, guarded by a locked door and a network firewall, the computing power is scattered across data centers globally. The immediate operational consequence of this architecture is absolute. The organization entrusts its critical information to hardware it does not own, and it no longer exercises direct physical control over its own infrastructure. Engineer William McFee once observed, "People don't ever seem to realize that doing what's right is no guarantee against misfortune." When an enterprise outsources the physical control of its hardware, following traditional IT best practices is no longer enough to guarantee security. Conventional IT security procedures rely almost entirely on defending a physical network perimeter. But when your data lives on a third-party servers located thousands of miles away, that physical perimeter disappears. Because the physical perimeter is gone, the enterprise's attack surface expands significantly. Securing the system requires abandoning hardware-centric defense strategies and finding a completely new locus for security enforcement. To mitigate this expanded attack surface, security cannot be treated as a final coat of paint applied to a completed system. Instead, the primary mechanism for defending cloud architecture is the Software Development Lifecycle, or SDLC. By engineering security requirements directly into the application during the initial design and coding phases, developers build protections into the code itself. This software-level security replaces the lost physical perimeter. The Cloud Security Alliance published the Security Guidance for Critical Areas of Focus in Cloud Computing, establishing the rigorous architectural rulebook for this exact transition. The Alliance divides cloud security into 15 specific domains. To navigate them, we first have to examine the concept of trust boundaries to see precisely how cloud architecture dictates our security obligations. Shifting hardware control to a third-party vendor strips away the physical safeguards. All critical security obligations are forced entirely onto the organization's software layer. This architectural stack diagram maps computing layers. A trust boundary is the exact line where provider responsibility ends and organizational responsibility begins. In an infrastructure as a service, or IaaS model, the boundary sits right above the virtualization layer. Here, your development team must secure the operating system, middleware, runtime, data, and the application itself. But in Platform as a Service, or PaaS, the provider manages the operating system and runtimes. Your developers focus strictly on securing the application code and the data it processes. Finally, Software as a Service, or SaaS, abstracts nearly the entire stack. The user is left with a minimal, highly specific set of controls, responsible almost exclusively for identity management and configuration. This dynamic is the core mandate of the Cloud Security Alliance's Domain 11, Application Security. A secure SDLC requires developers to account for these varying trust boundaries during initial development, testing, and the final production deployment of all applications. The deployment model dictates the exact location of the trust boundary. You cannot successfully secure an application running on IaaS if your developers are writing code based on SaaS assumptions. Moving down the stack from application trust boundaries, we find the foundational level of cloud storage. This requires evaluating domains 6 and 14 of the security guidance, which govern information lifecycle management and storage processes. This visualization shows a multi-tenant storage environment. In a public cloud, multiple organizations share the exact same hardware infrastructure. Your organization's data, the blue blocks, and another company's data, the green blocks, reside side by side on the same physical memory drives. In a shared architecture, establishing a physical air gap between the two organizations' datasets is impossible. Instead, the system relies entirely on logical segregation. Complex mathematical pointers map pathways connecting your data fragments, deliberately bypassing the neighboring fragments. These logical pathways are governed exclusively by the cloud provider's hypervisor and storage controllers. Because there are no physical walls between datasets on a shared drive, your security relies entirely on the mathematical perfection of these logical controls. This shared architecture introduces a critical paradox in the cloud incubation lifecycle: the massive gap between proving data retention and proving data destruction. Data retention is incredibly easy for a cloud provider to guarantee. By design, these networks utilize massive redundancy, constantly duplicating information to prevent data loss. Conversely, guaranteeing that data is completely destroyed in a multi-tenant environment is notoriously difficult. The assumption is that when a user issues a delete command, targeted data is permanently erased. In reality, cloud deletion works by severing the logical pointers linking data blocks together. It destroys the pathway, but does not actually overwrite the disk. The physical limitation is obvious. The cloud provider cannot pull the shared hard drive out of the rack and throw it into an incinerator. The other tenant's data is still actively using it. Your specific blocks are simply flagged as available for overwrite. Until a new user needs that space, your data remains sitting on the disk. The residual risk is severe. If the provider's logical controls ever fail, or if a vulnerability allows a malicious actor to bypass the hypervisor, that legally deleted data can be reconstructed and accessed. Deleted data remains physically intact on disks controlled by third parties. Your organization's lifecycle management is only as strong as its encryption keys and the mathematical boundaries keeping the tenants apart. This loop maps the software development lifecycle. Because you cannot verify physical hardware destruction, mitigation requires turning back to the organization's internal software engineering. Developers must architect software with the explicit assumption that any data written to the cloud might persist indefinitely on a shared disk. Domain 6 mandates that organizations deeply understand how the cloud provider's data destruction policies compare against their own internal compliance and destruction requirements. To audit the provider's claims, development teams execute rigorous backup and recovery verification protocols during the test and deploy phases. Regular scheduled testing probes the architecture to ensure that logical segregation and boundary controls remain mathematically effective, even after software updates or provider migrations. Security verification is not a one-time compliance audit. It is a continuous feedback loop that must be integrated directly into the software deployment pipeline. In a multi-tenant cloud environment where physical control is fully relinquished, security is not a perimeter you build. It is an intricate lifecycle of logical controls you continuously engineer and verify.